Hi, today I'm going to talk about clustering. So the algorithm I'm going to use are k-mean algorithm, spectral clustering, and principal component analysis for dimension reduction. So first of all, let's load the dataset. So this is a very classic textbook dataset. So you can see that there are 4 numeric variables and 1 categorical variables. And there are 3 categories in this column. So first of all, I need to standardize the dataset. The reason for that is that if if you don't standardize the dataset, you will see that the some data can be on a very different scales between different variables. So they can have a impact on your model. So let's say data with higher numbers can have more impacts or more significance in your model. That's what we don't want. So here we standardized the dataset so that after the normal transformation, you can see that all the data has been brought to the under the same scale, so that the unit or the scale will not affect the model. After the transformation, we can now start to further proceed to the modeling part. So actually, in R, there's a pre-built k-mean function which actually did a pretty good job. So as you can see that after running the k-mean, where we input our transformed data set and with the prior of k, which means that you need to know how many categories or what how many categories you think there should be in your data set. So so because I already know there are 3 categories, so I put 3 here, so that you can see that this is the cluster that the k-mean algorithm provided. So you can see that the first 50 data point are classified into the same category, and then there's some mixing between type 3 and type 1 for the next for the rest. And you can see that we also have the actual labeling for the category, so that you can see that first 50 are type 1 and the next 50 are type 2 and the rest are type 3. So as you can see that the k-mean algorithm did a pretty good job on separating the first category. Well, the numbers are different, but they means the same numbers means they fall into the same category. So our k-mean algorithm did a good job on separating the first 50 rows from the data set, but it did a poor job on separating the rest of the 2 categories, which the actual labeling should be like this, but our algorithm predicts something like this. So the k-mean didn't separate these 2 categories. We can also run a confusion matrix to see the prediction, but I'll just skip that. So beside using the k-mean, I also did a quick programming to run the k-mean algorithm from scratch, or to do it manually. So basically, the algorithm is that you put 3 initial random guess in the data in the space, and that you calculate the distance between for each data set between this centroid, and then for the minimum the minimum distance will be classified. So the distance with minimum distance to that centroid will be classified to that specific category. So so here I started so I just sampling 3 data set as my initial guess for the centroid, and then I create a placeholder to hold to store the distance for each rows for three categories. So I predefined there. So I told the algorithm that there are three clusters in this data set. So I'm going to calculate the distance for each data set for each rows between each data set to each centroid. So here I also and so for each iteration, I'm also going to update the centroid so that my centroid will gradually convert to the final destination where it describes the center or the centroid for that for each category. So while the two centroid are not converged, I will updating I'll keep updating the centroid. So as you can see that since this is a very small data set, so the algorithm converge or they look the same. I mean the two centroid matrix. So as long as they are not equal, and I calculate the distance between each rows to three different center. So here I'm taking the distance. So basically it's just the difference between two vectors. Take the square. Take the square and then sum them up, and then take the square root, which is the point-to-point distance in a space. And then I create a placeholder for the category, since there are 150 data. And then I capture the minimum. So I search if the minimum distance means that this data set belongs to that specific category. Then I update by taking the mean for the centroid. So for the data that fall into category 1, then the mean of those data will be the centroid for the new centroid. So let me so I can check. So after the algorithm converge, here are the actually it should be centroid new. Okay, yeah. So after converge, does it really converge? Okay, let me run it again. So that's what I start from, and this is what I end up to. No, this is what I start from by doing the sampling, and this is what I end up. So after a few iteration, and then the data, the centroid converge to this. So for the first type, for all the type 1 data, they have the centroid of this, and similar for the second and the third center. And let me take a look at the category. So as you can see that this is the one I get from this program. So as you can see that it also did a good job on separating the first category. So for the first 50 rows. So this is the same as the true label for this data set. So you can see that my algorithm, as well as the built-in k-mean algorithm, they all did a good job on separating the first 50 rows from the original data set, but they didn't do a good job on separating the rest of the two category, where this is the actual labeling. And then I can also show the model cluster. Okay, so this is what I get from doing the k-mean, you can say manually, and this is the actual labeling, and then this is the label, the cluster from the built-in k-mean algorithm. So as you can see that it shows the problem of what I just said. And so this is the one of the very popular classification algorithm. The drawback is that it only calculates the distance. So there are some special cases or difficult cases where k-mean will not work. And also, it also requires you to have a prior for the k, which means that you need to know, or you need to guess how many category will there be in your data set. So it is not normally we don't have the knowledge of k. So and also there's some paper talking about how to find the number of k. So this can be problems for some of the data set, or for some of the special cases where you don't have the prior knowledge on this. But it is actually a very popular algorithm, and it is a very simple one. So now I'm going to talk about another clustering algorithm that can handle different different scenarios compared to the k-means, which is spectral clustering. So that will require more math compared to the k-mean. So first of all, I need to there are 150 data point, and I'm going to create a placeholder for a matrix, which is called Similarity matrix, or there's some other textbook called adjacency matrix for other modeling, but the basic idea is the same. And here for this for this example that I'm showing, I'm going to use a similarity matrix, and I'm going to use a Gaussian kernel to group the data set. So basically, just exponential of the distance between two data point divided by 2 sigma squares. So this is like the exponential part from the normal distribution, the PDF. So basically, just that if they have more, if two data point have more if they are similar between two data points, and then they have higher, you can say, weight, or they have a stronger link between those two data points. So now let me run the algorithm. To create the similarities matrix, I'm using a Gaussian kernel. There are also some other method for to create the similarity or adjacency matrix. So you can look it up online for details on creating this. As you can see that I'm doing two nested for loops, so it might take some times to do the calculation. So after I have my working similarity matrix, there are some other steps or other calculation you need to do. So first of all, I'm going to calculate the degree matrix, which is basically the row sum for my similarity matrix, or if you have an adjacency matrix, basically well, it's the row sum. So basically just saying like how many connection between the first data point to the rest of the n minus one data point. So just their connection for each data point to the rest of the data. So the higher means there are more connection between this data point to the rest of the group. And then there's also a Laplacian matrix, which is d minus x. And then there are also some other standardized or normalized Laplacian algorithm calculation. So for the detailed, you can always Google it, or and then there are lots of tutorial or paper talking about this. So the normalized Laplacian is something the idea is something like we need to standardize the data set before we do the modeling. So so that's why we need to normalize it instead of using the regular Laplacian. But here I'm going to show you two different. I'm running the spectral analysis, spectral clustering on both Laplacian. So here I'm going to do the clustering, spectral clustering on the regular Laplacian, and then I'm going to do the same thing on the normalized Laplacian, and let's see how the algorithm is doing on these two on my predefined matrix. But first of there's one thing I need to point out is that this video or this tutorial is not going to show you how I can improve the k-mean algorithm, or how I can make it the prediction better. But instead, I'm just trying to show you there is some different method you can do when you have a clustering or classification problem. So like I said, there are lots of things you can do for your data set. So there are lots of different types of calculation for you to create your similarity matrix, adjacency matrix, or there are also different types of Laplacian. So there are a lot of things you can do to make it better. But for this video, I'm just going to show you that you have these options. But to make it better, you need to look into you need to understand your data, as well as to learn more about different variation of the algorithm to make better prediction. So here I'm going to make I'm going to get the eigenvalue and the eigenvector for my regular Laplacian, and then there's a error function that we are going to minimize it, and then the minimum the answer for the minimum. So the minimum, it is actually in the form of it is actually the eigenvalue and the eigenvector for the Laplacian. So the minimum of the eigenvalue will provide the minimum of the error function, and by taking from having the minimum of the a minimum eigenvalue and the eigenvector, and then you can do a k-mean on the eigenvector, and then it will provide you a clustering from the spectral clustering. So as you can see that so let me show you. So there are like so 150 data rows means you will get 150 eigenvector, and the minimum eigenvalue corresponding to the minimum eigenvector that will use a minimum error function, and then I'm going to do a k-mean on the minimum eigenvector. And now let's check. So this is the actual labeling, and let's take a actually this is the prediction that I get from the cluster from the spectral clustering, and this is the actual labeling. As you can see that the spectral clustering provides a better prediction on the labeling. As you can see that the first 50 are about the same, fall in the same category, except for there's some very issue on this one. And you can see that it provides more stable prediction on the second category. And then for the third category, there are some two showing in between, but comparing to the k-mean or from the k-means prediction, it provides a more stable prediction already. So so that's why we need to try different algorithm to get a different or to get a better prediction. And I will also show you later on why there's some mixing here, and then to give you a visualization on the mixing part on the these two category. Okay, so the regular so as you can see that the Gaussian kernel and on the normal Laplacian already provide a better prediction for to separate these three categories. So it is already very clear, except there's some mixing in between. So now let's take a look on the normalized Gaussian, normalized Laplacian, and there for the normalized Laplacian there's a different calculation. So we need to. So since I already know there are three cluster, I'm gonna take the top three eigenvector, and I need to also do a normalization on the cluster. Sorry, on my eigenvector, on my top three eigenvector, and then I'm going to do the k-mean on the eigenvector for the spectral clustering algorithm. So let's take the top three eigenvector, standardize it or normalize it, and then k-mean on my eigenvector. And now let's take a look. So this is the prediction from the normalized Laplacian, and let's take a look on the actual prediction. So as you can see that if it looks like it becomes more unstable than the regular Laplacian. There's some issue. Well, not all the algorithm is making it better, but it just a different algorithm or different calculation is used for a different scenario. There can be like a lot of scenario and lots of different algorithm for you to apply. So that's why we need to try always testing different algorithm, different calculation, different standardized method to get a better prediction. So it seems like in this data set, the regular Laplacian provides a better prediction than the k-mean, than the normalized Laplacian. So different scenario have different algorithm to apply to get for a different to get a better prediction. Okay, so now I'm going to talk about I'm going to show you or to visualize the data part, the data set. And now, so in here I'm going to I'm using a principal component analysis. I think I might have another video a long time ago talking about principal analysis regression. So and if you're interested in this used to be my favorite algorithm, and I so if you are also interested, you can take a look at that video. So basically, PCA is for dimension reduction. So let's say you have like 100 variables. So basically, that's like 100 dimension, and then applying PCA, you can make it up. You can reduce the dimension to, let's say, to 10. So to 10 dimension. So that you can have a simple model which includes only 10 variables instead of having like 100 variables in your model. So basically, the algorithm or the idea is also involving eigenvector or eigenvalue. So here I'm just calculating I'm just doing the manual steps on calculating the PCA. There are also the built-in function in R But I would suggest that you understand the math rather than just like using what other people developed for as a package. So so here, so basically the PCA will it's a dimension reduction method, and then it will tell you the variability that your principal component can explain to your original data set. So as you recall, there are four variables in your data, and then after some calculation, so I'll skip the math part or the algorithm. I'm assuming you understand the logic here. So you can see that the first three principal components, not the first three variables, the first three principal components can explain already like 99% of your original data. So actually, the first two components can already explain 95%. So there are lots of cutoff or threshold. So some of them, so in general, like 80% is already a good cutoff. But for demonstration, I'm just going to use the first two and the first three principal component for demonstration. So if you want to learn more about the math or the logic for this method, you can watch my previous video on the principal component analysis and PC regression to understand what this method is actually talking about. So so now I'm just going to take the first two principal component and make a graph here. So as you can see that, well, let me emphasize again, this is not first two variables, it's first two component, principal component. So as you can see that the first category, which I label red as red color, you can see that there's a clear cut in between from this category to the rest of the two categories. So this is the first category that we get, basically just 1 to 50 rows from the actual labeling. And you can see that even if I apply a principal component analysis, there still isn't a clear cut between these two categories. So you can see that there's some mingling, mixing between these two categories. So that's the reason why there's when you do k-mean or even spectral clustering, it is very difficult to separate these two categories. So you need to come up with a different clustering method to separate these two, so that you can have a clear distinction between type 1, type 2, and type 3. So this, even if we visualize it, and this shows that there's some there's some error in the prediction for the labeling between type 2 and type 3. Okay, so this is only viewing, so we are only using two principal component. We are viewing it from a two-dimensional space. So now let's take a look on the I'm going to use first three component, which represent 99% of the original data set. So I use a different a different package to make this graph. So here, sorry for the flashing, and then you can see that from the space with first three principal component, you can see that even in the three-dimensional space, there's a clear cut for the type for the first category. By spinning the space, you can see that there's a clean cut. So that's why the first category is always well separated from the rest of the group. And now let's see if we can keep spinning the graph and see if there's a clear cut between the distinct for the to separate these two categories. So it seems like um, still there isn't like a very clean separation between these two. So this is the reason why the classification algorithm are not providing a clear or like a so-called best prediction to separate these two category, because there's some overlapping between these two category. So there are also some other classification algorithm out there. So if you are interested on this problem, you can learn more on the different algorithms. There are supervised algorithm, unsupervised for those unknown k problems. So so this is what I have for today. So I hope you like the video, and if you like the video, please subscribe or share it to your friends for for uh, for tutorial purpose. Thank you very much, and let me know if you have any question on the algorithm or the math I did in here. So so basically, instead of using the built-in package, I use I do it mathematically by hand. So let me know if you have any question. Thank you very much.